When talking about limits, there are two different types of limits that we have to pay special attention to. Those are infinite limits and limits at infinity. Infinite limits are limits that have the function going to either positive or negative infinity. Here are two examples of that. Limits at infinity, however, are when the independent variable goes to either positive infinity or negative infinity, and what the value of the function is then. To start off, we're going to talk about infinite limits. If I'm talking about infinite limits, then what I would be interested in is what is happening around x is equal to 2, along this line. And just to emphasize the difference between infinite limits and limits at infinity, if I were talking about limits at infinity, as x goes to positive infinity, f of x goes to the number -3, and as x goes to negative infinity, f of x goes to 0. But again, right now we're going to focus on infinite limits, not limits at infinity. If we're given f of x, which is defined near but not necessarily at a point A, and we say that f of x grows arbitrarily large as x approaches A, then we write the limit as x approaches A of f of x is infinity. If, however, f of x grows arbitrarily small as x approaches A, then we write the limit as x approaches A of f of x equals negative infinity. But something very important to understand needs to be said. Although we write that it equals infinity or equals negative infinity, mathematically, the limit does not exist. But this is our shorthand way of talking about what happens when a function goes towards an arbitrarily large or an arbitrarily small number. On the example I have here, I can say the limit as x approaches 2 of f of x is equal to infinity. Again, we understand the limit doesn't exist, but it gets arbitrarily large, so we say as the limit approaches 2, the function goes to infinity. Let's look at negative infinity. Looking at the graph, we can say as x approaches -2 of g of x, this equals negative infinity. It's pretty easy to see this based on graphs. Just like we had one-sided limits when we were talking about finite limits, we can also talk about one-sided infinite limits. And we're going to write about it exactly the same way. The example I have up here, I can say the following. I can say that the limit as x approaches 2 from the negative side or from the left-hand side of f of x, that equals infinity. If I approach this from the other side, that is from the right-hand side, I would write it as such. As x approaches 2 from the right-hand side or the positive side, f of x goes to negative infinity. Let's look at one more example. In this case, as x approaches 2 from the left-hand side, g of x goes to negative infinity. And when 2 is approached from the right-hand or the positive side, g of x goes to infinity. Let's highlight this. This represents the limit of f of x as x approaches 2 from the left-hand side, and that goes to infinity. And this is what happens to f of x as x approaches 2 from the positive side. It goes to negative infinity. We can do the same thing for g of x. This is what happens when g of x approaches 2 from the left-hand side, and what happens to g of x when x approaches 2 from the positive side. I can say one more thing about these graphs of infinite limits. If f of x as x approaches A is plus or minus infinity, or the limit of f of x as x approaches A from the left-hand side, or as x approaches A from the right-hand side, if those are positive or negative infinity, then the line x equals A is a vertical asymptote. Let's draw these. I've added the line x equals 2 in both of those graphs. Those are the vertical asymptotes of those graphs. Let's go back to the previous graphs. For my first example, again, the vertical asymptote is x equals A. And for this example, the vertical asymptote is x equals -2. To be honest, usually we draw these as dotted lines. That's to show that the function never actually gets to that line. You can get very close to a vertical asymptote, but never actually touch it. Of course, we're not always going to be finding limits graphically. Sometimes we'll need to find the limits analytically based on algebra. So here's the limit as x approaches 2 of the function 1 over x minus 2 all squared. That's one of the graphs we've been looking at. Let's see if we could tell that this is going to go towards positive infinity without looking at the graph. Let's first look at it from the left-hand side. So as x approaches 2 from the left-hand side, that means x would be 1.5, and then 1.6, and then 1.7, 1.9, 1.999 as we got closer and closer to 2. That number subtracted from 2 would be negative, but because we square it, it's a positive number. So this approaches 1 over 0, and the denominator is always positive. So that means this is going to go towards positive infinity. Likewise, as x approaches 2 from the positive side, x would be equal to values such as 2.1, 2.01, 2.001. This time, the x minus 2 will always be positive, and we square it and it remains positive. So the limit as x approaches 2 from the right-hand side is also positive infinity. And as we've talked about before, if the left-hand and the right-hand limits go to the same number, then the limit going towards that number is in fact that same limit. In this case, infinity. Let's look at a second example. Let's look at the limit as x approaches negative 5 of 11 minus 3x divided by x plus 5. Again, we're going to be doing these without the graph, but I like to show the graph to show how it would look if we had examined this graphically. Let's first look at as x approaches negative 5 from the left-hand side. My numerator is not going to go to 0. It's going to go to, let's see, 11 minus 3 times a negative 5, that looks like it's going to be equal to a positive number. However, let's look at what happens to the denominator. As x approaches negative 5 from the left-hand side, that means x is going to be equal to, let's pick a small number close to negative 5 but to the left of it. Let's think of x equaling negative 5.01. That's just a little bit to the left of negative 5. If I plug that into my denominator, I would see that my denominator at x plus 5 is negative. Now that still approaches 0, but it approaches 0 from the negative side, so that means this limit is in fact going to be negative infinity. Let's look at this from the right-hand side. As x approaches negative 5 from the right-hand side, that would be x equaling something like negative 4.99. So now, just as before, my numerator is still positive, but this time my denominator, because 5 is greater than negative 4.99, that's also positive. So that means this limit is positive infinity, which means the limit at x equals negative 5, that I will write as does not exist. There is a trick to doing some of these. If I have something like this, the best thing to do is factor and then see if there's any way to simplify. If I go ahead and factor, I find I can easily simplify. Well, actually, I'm not done factoring. Let's completely factor the numerator first. Okay, that factoring didn't help that much, but that's all right. We'd still want to check. But I am going to go ahead and get rid of that x. Now, when x goes to negative 4 from the right-hand side, again, that would be something like x equaling negative 3.99. Let's see what happens. Well, in my numerator, I could go ahead and just plug in negative 4. And we'd find that my numerator goes to positive 42, the answer to life, the universe, and everything. But what happens to my denominator? Well, I've got a negative number with my x, and then my x plus 4, because negative 3.99 is slightly less than 4, I end up with a positive number. A negative times a positive is negative. So that means this whole thing is going towards negative infinity, because again, the denominator is approaching 0. And if asked, I could specifically say this implies that the function has a vertical asymptote at x equals negative 4, because the limit as x approaches negative 4 is infinite. So we want to find any vertical asymptotes and the following limits. So I want to find these three limits. Before I do, let's go ahead and factor g of x. So the x minus 1 in the numerator and denominator end up dividing out. And we find the limit of g of x as x approaches 1 is negative 1. It seems a little surprising because the denominator seems to blow up at that point, but let's look at a graph. If I graph this in Desmos and hover my mouse right over the point at x equals 1, you'll see that at 1, the function is undefined. It's a hole in the graph. It's not a vertical asymptote. So you always have to make sure that you do, in fact, factor first. Now let's look at the next two. Think of x equaling negative 1.01. The numerator, it looks like, stays negative since I have a negative minus another number. The denominator is going to be negative because when I add negative 1.01 to 1, I get a very small but a negative number. So that means the limit is positive infinity, and that matches what we see on the graph. And if we do the same thing from negative 1 to the right-hand side, you see that in that case the denominator is positive. And if we do the same thing from the right-hand side of negative 1, you see in this case the denominator is positive. Negative divided by a positive is negative, therefore that goes to negative infinity. Again, this is verified by the graph. That means my only vertical asymptote is at x equals negative 1. Let's do a quick last example, and that is with a trigonometric function. The limit of tangent as x approaches pi over 2. Now we could know what the graph of tangent looks like, but I could go ahead and rewrite tangent as sine x over cosine x. And by my quotient limit law, I know I could rewrite this as such. And at pi over 2, the limit of sine of x is simply 1, and the limit of cosine x as x approaches pi over 2 is 0. Well, hold on a second. I don't think I can just say that's equal to 0. I think I have to look at this from both the left-hand side and the right-hand side. So let's do that. First, looking at x approaching pi over 2 from the left-hand side, sine is still going to be equal to 1. And if I do a quick little graph of cosine, I see as we approach pi over 2 from the left-hand side, from the negative side, cosine of x is going to be positive. Again, it's going to be very small and close to 0, but it's going to be positive. Therefore, that limit is positive infinity. However, when I look at this from the right-hand side, I think I'm going to get a different answer. This time, as I approach it from the right-hand side, it looks like cosine is negative. Therefore, this one's going to go to negative infinity. And if I look at a graph, I see that's certainly the case. Again, we should be able to do this without graphs,